Hi guys, welcome to our channel of Sciences and Mathematics. Today's topic of discussion is going to be the concept of cell notations. And we're going to see that under the concept of electrochemistry, there are different ways in which we can be able to put notations for the galvanic cells that we have discussed in one of our introductory topics in electrochemistry. So for today, our topic of discussion mainly is going to be on how to illustrate these cell notations for different chemical reactions, of course, which we stated as spontaneous reactions that are resulting in a potential difference. So without further ado, thank you and welcome. So as I've said, today's topic of discussion is going to be basically cell notations. And we're going to see how different maybe reactions or maybe redox reactions can be able to be or can be represented in terms of notations. Maybe in a simpler way other than trying to draw the diagrams that we had already discussed, which are used to indicate the electrochemical cells. Now basically, as we said, the concept of electrochemical cells can be looked at in two different ways. We say that one, we have what we call a galvanic cell, which sometimes can be referred to as a voltaic cell. And number two, we say that we have another one that is known as electrolytic cell. And the major difference between the two is that the first one derives its energy from spontaneous redox reaction, while electrolytic cells involve non-spontaneous reactions. And thus, the second one requires an external source of energy, for example, like the batteries and other sources of electricity. So in this case, we're mainly going to concentrate on the first one and trying to illustrate on how we can be able to give a notation for that galvanic cell. And in a sense, we said that the galvanic cell basically consists of this type of electrochemical cell, which converts the chemical energy of spontaneous reactions into electrical energy that we have given another name for voltaic cell. Perhaps I have to give a demonstration, just a rough one for us to try and pick up from there, trying to illustrate how we can be able to give a notation for electrochemical cells. So those are two different setups for the concept that we had already discussed about the half cells. So I'm going to have just an illustration for that. So that basically is going to have our illustration for the general representation for a cell or an electrochemical cell, which of course we have said it as a galvanic cell. So in this case, we can be able to do a representation for this without drawing a diagram. But first of all, we have to know what constituents or what kind of details are entailed in this specific electrochemical cell. So in this case, we talked about the concept of an electrolyte. And basically, this is a solution that conducts electricity since it contains free ions. And it's made up of compounds which are able to dissociate in solution form and form free ions, like compounds like common salt, maybe sodium chloride, etc., which can be able to form free ions in solution form. So in this case, we're going to use the compounds for zinc sulfate. It's a salt zinc sulfate. And then this second one is going to form a solution of a copper sulfate. And we're going to use the two in order to illustrate how we can be able to give a notation for the electrochemical cell. Now, this electrochemical cell has got different parts. As you can see, we have had two different setups, of course, which are joined together using some junctions. So in this case, we're going to have this part of the cell. I can just maybe give a different, this one. So this part of the cell being illustrated or given as the anode. And this one is going to be the cathode. And having looked at those, there's this section in the middle here. This is known as a salt bridge. And we're going to see the reason as to why it is being referred to as a salt bridge. And basically for us, these are the two different setups that we're going to refer to as the anode and the cathode, respectively. So if we have those two specific half cells which are joined together, they form an electrochemical cell. Now in this case, we're going to use a redox reaction for those two specific setups to try and illustrate how we can be able to write the representation without using the diagram. So when I've talked about the concept of a redox reaction, this means there's reduction taking place, and then at the same time there's oxidation that is taking place. Now the reaction at the cathode, we're going to see that zinc comes first in the reactivity series of metals compared to copper. So therefore, zinc is going to be oxidized while copper is going to be reduced. So in this case, we're going to write a demonstration for that kind of a reaction, whereby zinc is going to form zinc ions by loss of 2 electrons, and then we are going to have copper ions being reduced to copper plus 2 electrons. And we're going to see that this general reaction can be represented using the reaction of zinc plus copper ions to form zinc ions plus copper. Like that. So in this two reactions, this is a general representation for the redox reaction. So in the first case, we are having an oxidation reaction, where in this second reaction, we are having a reduction reaction. So we can be able to allocate those two specific reactions for the anode and the cathode, respectively. Now there's this junction, a liquid junction that is formed in between this one that I've, or maybe a junction that I've referred to as a salt bridge. And this is a junction between two electrolytic solutions which form different compositions. And this is the junction whereby there is a potential difference that is formed that is known as a liquid junction. And of course it is noted. We talked about the concept of a potential difference, whereby we've already discussed about the concept of a standard electrode potential and how we can be able to illustrate that. So this salt bridge is going to form the bridge between the anode and the cathode, and there's going to be a potential difference that is going to be developed that you have of course called the liquid potential. I mean the liquid junction potential that is denoted using these 3 dots. So therefore, whenever we come across those denotations, this is referred to as the liquid junction potential. We're going to see that this one can be illustrated, of course, using a different way. And we'll see that whenever we're trying to measure the electromotive force that we've already discussed about in our introduction to electrochemistry, this liquid junction potentials interferes with the exact figures that we may want to obtain over the electromotive force that is being measured there. So this is countered or maybe reduced by the use of a salt bridge that we have illustrated there. Now basically a salt bridge is of course part of that electrochemical cell that consists of saturated potassium and ammonium nitrate. Just do away with this. So basically, as I've said, the salt bridge is a junction that it tries to encounter the effect of that electromotive force that is developed due to the liquid junction potential, in order for us to attain the actual or maybe the accurate figure for the potential difference that is happening between these two cells. Now this salt bridge is made up of potassium chloride and ammonium nitrate. which of course is compounded with they compounded with lithium acetate between the two solutions. Now, in this case, we are going to see that apart from this notation that we have talked about that represent the liquid junction potential, now the salt bridge that has been modified or illustrated or maybe introduced in this case to try and counter the electromotive force that is developing between those two, those two solutions of different compositions. We're going to see that this salt bridge is represented using those two. I can just use those two strokes for that illustration. So therefore, we are going to have a junction between the zinc sulfate and the copper sulfate solution using the ionic equation being represented as the section for the anode and the cathode being separated by this notation for the salt bridge. So therefore, if I were to have an illustration of what we have already illustrated on our right, I'm going to have the zinc sulfate interacting with that junction for the copper sulfate solution, the zinc sulfate and the copper sulfate solution using this specific illustration. But in this case, there are other details that we need to illustrate. For instance, the phase or maybe the state of this particular constituents of the electrochemical cell. So one of them is the concentration, and then the state. This is a solid, some aqueous of 1 molar, and then we have a salt bridge in between, and then we are going to have this ionic solution, and then solid. So this basically entails the representation or the short way or notation for the electrochemical cell, and it consists of it basically makes up a substitute for trying to write that electrochemical cell in terms of figures we have illustrated above. Now in this case, we're going to see that for the electrolytic, or maybe the cell that is comprising of half cells with the same electrodes and electrolyte. And when we were trying to illustrate this, of course, I can just put a simple illustration here. And this is a solution. We said if this is a solution that is an ionic form, it's going to form an electrolyte, which is a conducting solution, of course. It's a solution that conducts. Or can be able to just try to carry ions from one section to another. So in this case, because simply the ions are filling this solution, and this is what we call the electrode. Basically, it's a substance or an element which has been put into the solution and which can as well be able to carry charges, maybe like it can be a metal, or maybe carbon, and other conducting materials. So in this case, when we find that the cells that comprise of two half cells with the same electrodes and electrolytes have a specific name that we call concentration cells. So these basically concentration cells which have got two half cells with the same electrodes and electrolytes will be having various or a varied concentration or a varying concentration between the two cells. So therefore, there will be a potential difference between the two specific cells, and therefore there's going to be a flow of charges up to a point where the cells reach equilibrium. So this happens in a way that maybe the concentration at this particular point is trying to attain equilibrium by trying to concentrate the less concentrated solution on this other side, and this more concentrated solution decreases until the two sections of the two half cells reach equilibrium. So that's how the concept of concentration cells, as we may be able to mention it, happens. So of course we are going to see that this whole concept of electrochemical cells, as we said, can be illustrated or be quantified using the Nernst equation that we have already discussed in one of our videos, which we can basically just represent as E naught to 0.0591/2 the log of Q. So this is a general representation for the equation that we're going to use in order to quantify some of the aspects like the PD, or the potential difference or electromotive force that we're going to measure using these different kinds of cells. So in a sense, I hope that we have gotten the concept of cell notation using the illustration that we have given for the zinc sulfate solution and the copper sulfate solution. So basically, in trying to give a summary of what we have discussed in a statement form, I'm just going to give a small illustration before we wind up on the same. So I've said that we can be able to illustrate that diagram that is used to represent the electrochemical cell using a cell notation. And I've given the example for the zinc sulfate solution, which is of course forming another cell with the copper sulfate solution. And of course, there are respective redox reactions which are going to occur. In this case, of course, we have said can be represented using the ionic equation, whereby the copper ions are going to be displaced, and then we're going to form zinc ions plus copper. This is aqueous. And we have said that this process that is forming the zinc, this is going to be oxidation, and the copper ions, this is going to be reduction. And therefore this redox reaction can be represented in form of a cell notation, which we have said it can be written as the zinc is undergoing oxidation to form zinc ions. Of course, we said for us to represent the cells, you write the state or the phase of those particular species which are undergoing redox reaction together with their concentration. So in this case, for a standard one, we said this is going to be molar, and then copper. So just like that. So in between this cell notation, there is a symbol which we have said, and I've referred to this symbol as a salt bridge, which basically is made up of, as I said, saturated sodium chloride or ammonium nitrate. Potassium chloride or ammonium nitrate. For the simple reason that this is going to assist in trying to counter the junction potential, the liquid junction potential, which is created due to the, of course, the differences in electrolyte concentration between the two half cells. And this, of course, can be able to be used in conjunction with lithium acetate. And this salt bridge, as we have said, of course, is joined between the two half cells, as we have illustrated. Now, maybe we are going to use different examples in order to illustrate how we can be able to quantify this kind of, or maybe illustrate on how we can be able to represent as well the cell that we have talked about in our discussion about the Nernst equation from this particular representation. So in that case, of course, I hope that we have understood about the concept of representing these spontaneous redox reactions in electrochemical cells, which of course can be represented as our last illustration that we have talked about. We're going to do more examples on the same and try to see how we can be able to write that one in conjunction with the standard electropotential concept that we have discussed in one of our videos on electrochemistry. So that is it for today, guys. Bye. God bless.